Hello students, I am Partha Chakraborty from Department of Geology, University of Delhi. Today our topic of discussion is radiogenic and stable isotopes and their role in the sedimentary geology in terms of the paleoenvironmental interpretation, paleoclimatic interpretation, source area interpretation, like that. Once you will go through this course or then you will come to know that what is basically meant by the radiogenic and stable isotope. What are the processes that make them useful for use of paleoenvironmental or paleoclimatic study from the sedimentary rocks. You will also able to comprehend that how the different kinds of the geological material, the natural material that help us in doing the exercise by use of these isotopes. So, if we go by this course, then we will first say that what is a isotope. A isotope is that of a element which varies in their neutron number. So, that what we call the isotope, but it has the same proton number. So, the neutron numbers are different, but the proton numbers are same. In that case, you get that each element can make a number of isotopes. The simple example is that of hydrogen. You can have the hydrogen, the deuterium, the tritium. So, these are the variation in the neutron number, though proton number remains same. Like that, there are in nature the large number of isotopes which from which some of the isotopes are of use for our geological purpose, which I will be discussing today. So, what is isotope? The isotopes are those of a particular element which vary in their neutron number, and accordingly they have their different kind of character. Now, fundamentally what isotopes are? Which do not vary in terms of their electron or valency. So, as they do not vary in their valency, so I should not expect much of the difference in their chemical character, but they vary in their neutron number. So, if their neutron number varies, so their physical character also definitely varies. And accordingly, the isotopes are classified into two different types. One is radiogenic isotope, which basically decay and with a half life, that I will discuss in detail, that there is a decay process involved, and there is other isotopes which are stable isotopes which do not decay. We take use of both the isotopes for our different purpose. In the next discussion, I will be discussing in detail that how these different isotopes, radiogenic and stable, they help us, and what is their mode of operation and how it helps that in the different kind of purpose for our geological interpretation. Some examples of these radioactive isotopes are such as uranium has two isotopes, that is uranium-235, which consists of 92 protons and 143 neutrons, and uranium-238 consists of 92 protons and 146 neutrons. Uranium-239 is obtained after the bombarding of uranium with slow electrons. The half-life of radioisotopes uranium-239 is of 23 minutes, and it disintegrates beta particles to produce new element known as neptunium with mass number 239 and atomic number 93. Some other example is plutonium, which has two isotopes, that is 241 and 239, and they disintegrate to give two important transuranium elements such as americium and curium, where americium has a mass number 241 and the atomic number 95, curium has the atomic number 96 and mass number 239. Now, these radiogenic isotopes, they basically decay in three major processes. One is called alpha decay, then beta decay and the gamma decay. In alpha decay, an atom ejects two neutrons and two protons from its nucleus, and thereby the atom decreases by 2 in its atomic number and the atomic mass by 4. In beta decay, basically a neutron turns into proton and an electron is emitted, and in that case the atom increases by its atomic number by 1, but the mass decrease is only slight. Gamma decay takes place when there is a neutron capture or residual energy left in the nucleus following alpha or beta decay in a nuclear reactor. Now, where we apply, as I have already discussed, that where we normally apply and why we at all apply the radiogenic isotopes. We apply the radiogenic isotopes for tracing the source and transport of dissolved and detrital constituent. We also apply it for reconstructing the temporal changes in ocean water chemistry and apply these changes in the stratigraphic correlation and temporal changes in the hydrologic, sedimentary and biogeochemical cycles, and for dating the time of formation of a rock and mineral. Now, among the different radiogenic isotopes, the two most important radiogenic isotopes what we use in sedimentary column, these are strontium and neodymium, and they are used in the paleoclimatic study as well as the study of the age of the ocean water, the seafloor spreading activity and like the other issues. Now, their use in paleoclimate can be discussed when we discuss their pattern in the rain, surface water, ocean and its role in the climatic factor. If we see rain, in the rain strontium is only a volatile element. Strontium is only a volatile element and it remains in the ocean during the process of evaporation, due to which the strontium concentration of rainwater is very low. The strontium concentration also decreases from coast towards the interior of the landmass, and in the surface water, in comparison to the other major ions such as sodium, calcium, magnesium, the composition of strontium isotope reflects a first order control by geology, that is the rock type and age of the area that they drain. In oceans, which is the ultimate container for the surface runoff and the hydrological cycle that drains all the sediments from the continents, the oceanic composition of strontium isotope reflects the respective fluxes of the agent of transport of the hydrologic cycle. The most common difference between the geochemical behavior of neodymium and strontium, which affects the nature of their oceanic records at the short time of residence of rare earth element and the attendant heterogeneous neodymium isotope pattern in the modern oceans. These differences have the edge of using neodymium isotopes in marine deposits as tracers of the provenance of dissolved RE and oceanic currents within and between the ocean basins. Now, in the climate research, the global climate change has come in a major way of discussion in today's life, and the stable isotope analysis as well as that make a major role in the process. We normally do this in the ice core and the corals. Isotopes are thus powerful tool even for the climatic study. Now, this figure is an attempt to show you how the fractionation of isotope in the different process that should be taken into account when we will be doing any isotopic study. This is the ocean, that is the reservoir where you can see it is the 0 parts per mil. From that ocean, in the hydrologic cycle, when it is going and the ocean water is evaporating and the cloud is forming, you can see that the isotope there it becomes that is minus 10 parts per mil. The same when it goes in the form of rain, that is about minus 3 parts per mil. That from the continent, when the evapotranspiration, that is showing minus 7 parts per mil. In the vapor it is minus 15, in the precipitation minus 5. So, the aim of this figure is that whenever we study isotope and then use it, we should take into account the fractionation effect of the isotope because of the different phase behavior, and that is very important in not only the as we know the temperature, moisture content, everything has a role to play, but definitely the fractionation between phases that should be taken account of. So, some of the uses of radiogenic isotope that we use commonly in the oceanic the seafloor spreading activity that we can monitor, and we can say that the past oceanic seafloor activity, the oceanic crust formation, that is done from the strontium isotope. What happens really that in strontium isotope, the strontium 87 and strontium 86 that will, and strontium 87 that basically is coming from the rubidium. And because the rubidium that essentially remains in the replacing the calcium in the feldspar structure. So, basically the source of strontium 87 that becomes the continental crust, whereas the strontium 86, which is basically the primary reservoir and is related to the mantle activity. So when by monitoring in the ocean core sediments that what is the role of strontium 87 by 86, we can clearly identify that the relative role of continental supply and relative role of the mantle supply or the erosion of the oceanic basalt or the oceanic island. So these two are the counterpart, that is one at a time when the continental derivation is more in the ocean column and sometime when the mantle derived material that is more in the ocean column. How these things that vary with respect to time, the strontium is a major thing, that the higher the 87 SR, the more is the continental supply, where the higher is the 86 SR, then we get the more of the mantle supply by means of the. Now this is also helps us to identify under the monitor and talk about the sea level changes. Now if I monitor the sea level changes, that we know that the sea level changes that causes the river system to go away when there is a sea level rise or the sea level for the river system approaches towards the shoreline, and that basically control the what is the detritus supply within the ocean column, and depending on the detritus supply in the ocean column, that the strontium isotope ratio that also is variable, and there is a large scale long term pattern of these changes that basically help even in the different kind of cyclicity of the sea level change that people talk about. Now coming on to the neodymium isotope. Neodymium isotope is considered as a major proxy for identifying the source area. There is a evolution trend of the mantle in terms of the neodymium content. So there is 147 and 144 and 143 neodymium. These three help us in identifying that what is the proper source area, because the rocks of the different time domain, they vary in their neodymium isotope character, and that isotope, that is particularly the EPSA ND value, that help us in identifying that what is the source area. And suppose in a sedimentary column I have the different kind of sediments, and then that is not very clear that two different sandstones, they are coming from the same source or they are coming from the different source, which may not be clear to you because of the same mineralogical content. Just take an example, I have a Archean granite and I have a Proterozoic granite. Both are mineralogically, it is the quartz and feldspar. But in a basin, that at one point of time the Archean granite is supplying the sediment, and the other point of time that the Proterozoic granite is supplying the sediment. Now how I can say, if I see the mineralogy, that the one time the Archean granite is supplying and another time the Proterozoic granite is supplying. One major proxy in this case is the neodymium isotope and the EPSA ND value of the Archean granite and the Proterozoic granite, that will help us in identifying that these are the products of the two different time plane. They are supplying provenances were different in times of the time. Now coming on to the stable isotope. Stable isotope has a major role to play in case of sedimentology, and particularly the stable isotopes are extensively used in case of the carbonate, the oxygen isotope, the carbon isotope, these isotopes, and also in some cases the stable isotope, the sulfur isotopes are also being used. Now stable isotope fractionation, it depend on some chemical and the physical processes. Suppose even the biological processes, the biological such as photosynthesis, the chemical that is evaporation or the condensation. So all these processes, they also affect the stable isotope, the fractionation, which depends upon the temperature and isotopic ratio of the two reservoirs. So depending on that there will be the change fractionation of the stable isotopes, which when we see a particular sample and we try to identify what is the stable isotope ratio in terms of some kind of a standard, and that's suppose when we do the oxygen isotope, we can do it with respect to SMO, that is the standard mean ocean water, or we do it with the PDB standard, that is the PD belemnite standard. So accordingly these two major standard, this standard with respect to standard, what is the variation in the sample, that basically we model, and that we say the delta, that is the isotope ratio within the sample divided by isotope ratio in the standard minus 1 into 1000. So this basically is the formula that we use for any to monitor that what is the isotopic fractionation or what is the isotopic variation with respect to standard in a sample. Now with stable isotope, the two most fundamental parameters that is needed to study climate dynamics and the evolution of the climate system are marine sea surface temperature and the hydrologic cycle. Accurate reconstruction of these elements is essential for use in climatic model, which are then used as a basis for testing hypotheses concerning the issues of climate change. The stable isotope techniques are often applied to both sediments and fossils such as lake sediments, ostracods, coral reefs, fish teeth, like that. Now the stable oxygen and hydrogen isotope composition of precipitation is strongly influenced by the temperature and moisture sources. This I have already discussed. Thus records of del 18O and del 2H hydrogen based on material produced within lakes can provide insights into past climate, as long as the isotopic composition of the analyzed sediment component reflects the former isotopic signature of the water in which it was formed. We will discuss a few examples for the reconstruction of the paleoenvironment in application of stable isotope theory. Now, so example 1, I want to discuss about the ostracoda, which is often used. The ostracoda are small size crustaceans and they range in size about 20 μm to 32 mm. Adult species are in the range of 0.7 to 1 mm. Ostracods are adapted to a wide range of salinity, so their natural habitat spans from the lakes to open ocean, which help heavily in making this exercise successful from ostracod. There are also some rare terrestrial species also. The importance of ostracod grows exponentially for those environments in which foraminifera are rare or lacking. In some cases, the presence of amorphous calcium carbonate reports and the remainder of the carapaces represented by organic material. It is widely accepted that the carapace composition reflects the host water chemistry, because ions that form the shells and directly taken from the host water. The ostracod's vital cycle requires 8 to 9 molts before reaching the adult stage, with the very short duration of calcification after each molt. This we take into our advantage, and that help in the study of the ocean water chemistry. The vital offset that influence the carbon isotope of ostracod valves are still not completely understood. However, it is seen to create systematic variation. It is clear that the use of ostracods entails several advantages as well as some disadvantages. However, they are considered as one of the most reliable indicators for marine and non-marine settings. The use of ostracods by the stable isotope study we mostly do for because the ostracod valves are quite easy to be separated. They have a low Mg calcite mineralogy. They are fully abundant marine in non-marine sediments. Ostracod cells reflect characteristics of the water in which they grow, and ostracods molt several times during their lifespan, and that helped in the paleoenvironmental reconstruction. Now, we also use the stable isotope in the coral reefs, and mostly they are aragonitic in mineralogy, but they are annual growth ring that helps in the monitoring of the climatic signal. The corals build and they grow with the annual density bands that they produce, that help in the development of the chronology. Now, we normally do the oxygen isotopes in that. The ratios of isotope species of oxygen 18/16 incorporated in the coral skeletons during their growth, that is reported as del 18O, and are primarily influenced both by temperature and the del 18O of the ambient seawater during skeleton precipitation. In localities where one of these two environmental factors dominate the other, The coral 18 REL 18O records can therefore provide information either on variation in water temperature or the variation in the seawater that is known. The temperature increases, as the temperature increases, there is a decrease in the del 18O of the coral skeletal aragonite. Near weekly resolution calibration of porites coral del 18O variability suggests a temperature dependence of 0.18 parts per mil per 1 degree centigrade. The isotopic disequilibrium that we get from the coral that is assumed to be constant over time along the major growth axis of an individual coral colony, where growth and calcification rates are at their maximum. However, long-term trends reported in some coral del 18O based studies are consistent in sign but too large to be explained by observed changes in sea surface temperature, seawater salinity or rainfall over contemporaneous intervals. Use of the stable carbon isotope. The environmental interpretation of the ratios of the stable isotope species of carbon incorporated in coral skeletons reported as coral del 13C is complicated because the interactions with physiological processes such as symbiont photosynthesis and respiration. The application of the coral del 13C signal as a climate proxy has been hampered therefore, and despite the fact that the del 18O and del 13C values are routinely produced together by mass spectrometry. This trend most likely reflects that the del 13C of the dissolved inorganic carbon of the seawater is usually attributed to the corresponding trend of the del 13C of the atmospheric CO2 owing to an increase of anthropogenic release of 13C depleted CO2. However, the slopes of the trends differ among coral records even for individual corals from the same location. So, the seasonal cyclicity in coral del 13C is sometimes used for age model improvements of coral records, where a clear cyclicity in coral del 18O is absent due to local environmental conditions. We also take the help of this in the lake sediments, and stable isotope analysis of organic material produced in lakes and their surroundings provides information on past climate and ecosystem. So, organic fossils originating from invertebrates contain elements commonly analyzed in stable isotope analysis such as hydrogen, carbon, nitrogen and oxygen. The potential of stable isotope analysis in invertebrate fossils for paleoecological reconstruction was pointed out more than 20 years ago. However, to date only a few attempts has been made to analyze stable isotopes in chitinous remains preserved in lake sediments. Advances in stable isotope techniques and instrumentation have significantly decreased the sample mass required for an analysis. Subsequently, fossils originating from different taxonomic groups such as different species, different genera, different subfamilies of aquatic invertebrates can be analyzed separately, and this opens up a range of potential applications in paleolimnological research. So, what we have discussed that in India we get about 26 major sedimentary basins, and which we have characterized as per the norm of DGH into 4 different categories. And the aim of this my discussion, that is basically to characterize the basins in terms of their hydrocarbon prospectivity. So, before I go into the discussion of some of these basins in detail, first we must see that what are the features that makes a basin hydrocarbon prospective. I should have a proper source rock, should have a reservoir rock, and there should be a proper pathway from the source rock to the reservoir rock that we have already discussed in the other modules and the discussions. Now, what I call a source rock? So, source rock is that which is a fine grained rock and where there is a significant accumulation of organic matter. This organic matter should be of very specific quality, which I already have discussed in the other module, that for hydrocarbon generation I should have a organic matter which has a high hydrogen is to carbon ratio, that means type 1 or type 2 organic matter, as per we have discussed in the Van Crevelen diagram in the other module. So, proper kind of organic matter which has a high H is to C ratio, and also that organic matter should go through the proper kind of maturation process, that is the temperature pressure profile. So, all the 3 things, that is the proper accumulation of organic matter, of proper quality and their proper thermal maturation history that will make that source rock prospective in a particular area. And as you know, when you talk about the proper thermal history, that depends upon the subsidence history of the basin and the geothermal gradient of the basin. So a scale of subsidence and the geothermal gradient that basically controls that what will be the temperature that will be available at a particular depth in that basin. Also it is important what is the age of the basin, because that is finally the temperature and time that makes the basin, the organic matter cooking, and that creates the proper condition for the hydrocarbon generation. Now besides this, what is important that I should have in a basin, that is the reservoir rock. Now when we talk about a reservoir rock, what is a reservoir rock? A reservoir rock is that which has the proper porosity and permeability. And porosity, what we already described, that it is basically the void space within the rock. So you have the, how we describe the porosity, the total volume of void space divided by the total volume of the rock. So porosity doesn't have any unit, but it is expressed in percentage. Now porosity again can be two types, that is the primary porosity and secondary porosity. Most of the clastic reservoir, that is the clastic rock, what we get the primary porosity, whereas the secondary porosity is very important in the carbonate rocks. I am not going into the detail of the secondary porosity. You can have a interparticle, fenestral, moldy, cavernous and fracture. All these different kind of secondary porosity is what we can develop even in a carbonate rock. Now when we talk about a reservoir and a trap, what is the difference between a reservoir and a trap? A reservoir is that which has the proper porosity permeability condition that can be suitable. If the oil is available, it can hold the oil, and the proper permeability that it can yield the oil. So it can hold the oil by in its porosity and it can yield the oil by its permeability. Any rock that has that quality, we call it a reservoir rock, but it no way means that that rock contains oil or not, but it has the quality of holding and yielding oil. But when oil is physically present within a reservoir rock, then we call it a trap. So when there is a physical entrapment of oil in a reservoir, then the reservoir is termed as a trap. This, the other quality of a reservoir, what I have also mentioned, that is the permeability. Now what is the permeability? Permeability is the interconnected pore space. So more the interconnected pore space, then the rock will have the more permeability. And the permeability is the property of the medium. Mind, permeability is not anyway property of the fluid, but it is the property of the medium. So the porosity and permeability, these are the two things that make the reservoir any rock the proper kind of reservoir, or if the oil is available, the trap. Now again for the trap, there are three different varieties of trap that people have talked about: stratigraphic trap, structural trap and combination trap. Now stratigraphic trap, what are those? Stratigraphic traps are those where there is a vertical or lateral variation in the permeability. If the oil has come but it cannot go because there is a low permeability rock on its side or above it, then you call it a, so that means the low permeability rock that is acting as a cap. So any trapping of the hydrocarbon that not only requires only the source rock and the reservoir rock, but also it requires a cap rock. And that cap rock is nothing but a low permeability rock which do not allow the hydrocarbon to pass on continuously, so there is an entrapment. So stratigraphic, this is what, there are many ways, there is a wedge out, the lenticular bodies, the channelized bodies, so all these are the examples of the stratigraphic trap. The structural trap, where there is a structural closure, it can be fault related, it can be fault related, it can be fold related. So the stratigraphic, the structural trap that is created by the tectonism and any kind of structure, that is formed as a structural trap in an area. A combination of stratigraphic and the structural trap that we call the combination trap. That means suppose there is an unconformity. The unconformity, that is basically the stratigraphic trap, that across the unconformity the lithology changes. So the oil, if it is coming, so the above the unconformity, the less permeable rock, it may not allow it to pass by. Now, this unconformity then found to be by later tectonic activity to be folded. So, then we call that as a combination trap that so when we go to the discussion of the different Indian basins, we will see that there are rocks which has the proper reservoir quality, there are rocks which has the proper source rock quality, and there are rocks within that which has the proper cap rock quality. A combination of these that has made those basins a particular kind of petroleum system, such as we will discuss the Assam Shelf and the other basins also. So, students, we have discussed that what are isotopes and how the isotopes they help us in interpreting the different paleoenvironmental issues and the paleoclimatic issues. We have seen that the most of the use of the isotopes are three major use. One, that what is the source of a sediment of any dissolved material or a detrital material that we normally trace by means of the isotope. Also, we try to interpret any change in the climatic condition in the past. So, past climatic changes, that also we try to interpret from it, and also we try to interpret in terms of some correlation of the reference strata, and that correlation history that we also try to make out of the isotope. So, there are different isotopes which are used for this purpose, but two isotopes which are very useful for us for understanding the seawater composition, its temporal change, its secular variation, as well as the correlation of the strata that are deposited through the marine system, those are the strontium and neodymium. We have discussed their role in terms of both the issues. We also have discussed the role of oxygen and carbon stable isotopes in terms of the identifying that the temperature variation, the moisture variation, and also the use of carbon isotope in terms of the identifying the productivity change in the ocean column, and all these different kinds of issues that are related to the paleoenvironment and the paleoclimate. So, isotope in sedimentary geology, it helps in a large way as a proxy for many issues which we do not often doesn't remain solved by the simple field geology. It is a good help to make the field geological observation more robust, and that help us to identify that many issues that particularly related to the source issue, which are very important for any kind of sedimentary strata by means of the neodymium isotope, the strontium isotope that help us in the seawater column composition, and the oxygen isotope which help us in the temperature variation and also in the history of the glaciation and the deglaciation. So, all these issues that what we address by the isotopes that we have discussed today, I hope you have enjoyed the discussion that how isotope is used in the different issues, and this will encourage you to go through the further literature in future. Thank you.